So in the previous lecture, we defined connectedness. So we shall continue with that discussion. So we put an equivalence relation on the points of x in the following way. So we say x is equivalent to y if there is a connected subset T of x which contains both x and y. So let us check this is an equivalence relation. So we have to check three things. First is x is equivalent to x. So this is clear as we can take T to be the set. So a singleton set is obviously connected. So therefore, so the second condition is if x is equivalent to y, then we have to show that y is equivalent to x. But this is also obvious because x is equivalent to y implies there is a subset T, connected subset T, which contains both x and y, and that same subset will work for y equivalent to x. And the third condition we want to check is that if x is equivalent to y and y is equivalent to z, then x is equivalent to z. So this follows immediately from the following lemma. So let T1 and T2 be two connected subsets of x such that their intersection is not empty. Then their union is connected. So the proof is left as an exercise. So these three conditions show that. So from this lemma, condition 3 is immediate. And so thus, tilde is an equivalence relation. On the points of x. So recall that every time we have an equivalence relation on a set, it breaks the set into, so it breaks x into a disjoint union of subsets. So these are called the equivalence classes. Each of these subset is called an equivalence class. So this will be denoted X breaks as a disjoint union of I and I of these xi. And each xi is equivalence class of some x. Of some x. Okay. So we have this proposition. Every connected subspace of X is contained in some equivalence class. And the equivalence classes are maximally connected. So of course we shall explain what maximally connected means, but it should not be hard to guess. And closed subspaces. So the equivalence classes are maximally connected and they are also closed. So let us prove this proposition. So to prove the first assertion, so let T be a connected subspace of X. Yeah. Now suppose T meets Xi and T meets Xj. Right. So that means so let T belong to T intersection Xi and S belongs to T intersection Xj. So then uh, T is equivalent to S as capital T is the connected subset which contains both S and T. So this will mean that, so this will imply that the equivalence class of T, which is Xi, is the same as the equivalence class of Xj, of S, which is Xj. Right, but if Xi is different from Xj, this is a contradiction. So this implies that T is contained in Xi or Xj. So this gives a contradiction. So this gives a contradiction. So if Xi is different from Xj, then this gives a contradiction. So this proves the first assertion that uh, every connected subspace is contained in one equivalence class. Next, let us prove that each equivalence class is connected. So let Xi be an equivalence class. And let X belong to Xi. So we fix an X. So then for every Y in Xi, by the definition of equivalence classes, uh, Y is equivalent to X, and so there is a connected subspace t sub y of x such that x comma y belong to t sub y. So clearly, from the previous part, it follows that t sub y is contained in xi, and then that xi is connected follows from the following variant. So this is a slight modification of the above lemma. So let me write this, and this also left as an exercise. So let Ti be a family of connected subsets of X, and suppose the intersection of all I, Ti is non-empty. So all these Ti's they meet at a point. So then the union of Ti's is connected. So this will imply that the union of all the Ty's is connected, but the union of all the Ty's is exactly Xi. Okay, so this proves the second assertion. Next, let us show that each equivalence class is maximal connected. So what this means is that suppose T is a connected subspace of X such that it contains some Xi. So then by the first assertion, this implies that T is contained in some connected component. T is contained in some equivalence class, but then that has to be equal to Xi, which has to be Xi. So this implies that Xi is equal to T. So it's maximally connected in that sense. And finally, let's prove the last assertion of the proposition is closed. So as Xi is connected, this implies that Xi bar is connected. The closure is connected. This is what we saw in the previous lecture. So this implies that Xi is equal to Xi bar using the previous what we just proved. So which implies that Xi is closed. So definition: the equivalence classes are called the connected components of X. And as an exercise, easy exercise. So let Q contained in R be the subspace with the subspace topology. So what are the connected components? So we make a remark: X is connected if and only if it has only one connected component. So So this remark is clear. So this brings us to an end of the discussion on connectedness. So now let's define a slightly more intuitive construct. Well, we will later see that it's a stronger notion. Definition: path connected. So let X be a topological space. We say X is path connected if for any two points X and Y in X there is a continuous map. So this is what is called a path. Gamma from 0, 1, a continuous map gamma from 0, 1 to X such that gamma of 0 is X and gamma of 1 is Y. So this is that there is a continuous path from X to Y. Yeah, so the picture can look something like this. This is X, this is small x. So this is gamma of 1, this small y. And gamma can be any complicated path. So it should just end at y. So we have the following obvious proposition. A path connected space is connected. So prove. If not, assume X can be written as U disjoint union V, where U and V are non-empty open. So let X be in U and Y be in V, and as X is path connected, gamma from 0, 1 to X be a path from X to Y. So then we can write, we just pull back the open subsets. So this contradicts the connectedness of 0, 1. So obviously, so 0, 1, the real line, Rn, S1, Sn, all these are path connected. All these are path connected. So these will be exercises in the tutorial sheets. Okay, and as before, we can define an equivalence relation as follows. So X is equivalent to Y if there is a path gamma from 0, 1 to X such that gamma 0 is X and gamma 1 is Y. So once again, let us check this is an equivalence relation. So X is equivalent to Y, this is clear. So take the constant path. which is obviously continuous. If x is equivalent to y, then we have to show that y is equivalent to x. So we start with gamma, which is the path from x to y, and then take delta of t, define it to be gamma of 1 minus t. Then delta of 0 is y, and delta of 1 is x. So this is just, we just travel the path gamma in the reverse direction. So, and the last condition we have to check is that x equivalent to y and y equivalent to z implies x is equivalent to z. So x is given equivalent to y, so there is a path from 0 1 to x such that it ends at y and begins at x. Similarly, there is a path which begins at y and ends at z. So we are going to do the following. So the idea is to travel gamma 1 at twice the speed from 0 to half, and then gamma 2 at twice the speed from half to 1. So we'll define a map from this to x. So define h1 to x by h1 of t is equal to gamma 1 of 2t, and h2 half h2 of t is equal to gamma 2 of 2t minus 1. So this is A and this is B. Both A and B are closed subspaces of 0 1. And okay, so and h1 and h2 are continuous. Y, and moreover A intersection B is just a singleton half where h1 and h2 agree. So thus we can put h1 and h2 together. We can join them. So this is the last theorem in lecture 9, and define a continuous map from 0 1 to x, which sends 0 to x and 1 to z. So this proves that this tilde is an equivalence relation. So using this, so once again we can break it into equivalence classes, and each equivalence class is called a path component. Path components. So once again we have a similar proposition. Each path component is maximally path connected. And every path connected subspace t contained in X is contained in a path component. So proof, imitate the earlier proof. So this is left as an exercise. Left as an exercise. So a notable difference between the two propositions is the absence of the word closed. So path components need not be closed, as the example below shows. So it is also natural to ask if path connected is equal to being connected. So the following example shows this is not the case. So let us consider this example. So consider this space C. So I will make a picture which makes it clear what it is. Union so the space it looks like this. So the origin is deleted and this is 1, so this picture is not up to scale. So this point, let's call this point P. And at each 1 upon n, so this is 1 by 4, this is 1 by 3, this is 1 by 2, so there's 1. At, at each 1 by n, we take the vertical line up to length 1. So our claim is the following. So let gamma from 0, 1 to C be a path such that gamma of 0 is the point 0, 1, which is the point P. And then we claim that for any such path, the image of gamma is contained in Y. So Y is this subspace. So this vertical line is Y. And this whole set we call C. So let us prove this. So let us assume, we'll prove this by contradiction. So let us assume that the image of gamma moves out of y. So now y is closed, and that is like trivial to check, and therefore it's left as an exercise. As y is a closed subspace of C, so check this, it follows that gamma inverse of y is a closed subspace of 0, 1. So we consider the subset S, which is those x in 0, 1, such that gamma of this closed interval is contained in y. So clearly S is non-empty because 0 belongs to S. So we let T naught be equal to supremum S in S is. So first we claim that gamma of T naught belongs to y. So note that there is a sequence T ends in S such that T ends converge to T naught, and as gamma is continuous, so this implies gamma of Tn converges to gamma of T naught, and as y is closed, this implies gamma of T naught belongs to y. So if T naught is 1, so then this proves our claim that gamma of this whole thing is contained inside y. So let us assume that let us assume that T naught is strictly less than 1. So we take a small open set U around gamma of T naught, which does not contain 0, 0, the origin. So the picture is like this, so maybe I can make it in a different color. So this is gamma of T naught. So we take a small square like this, a small open set. So then gamma inverse U, so it's an open subset which contains T naught, and therefore it contains a small neighborhood of T naught. So in particular it contains an interval of this type for some epsilon positive. So as T naught is the supremum of points in S, so this implies there is delta, which is in this open interval T naught plus epsilon, such that gamma of delta does not belong to y. So once again, this just follows from the definition of S, and and supremum. So check this. So this implies that gamma of delta uh, it is of this form: 1 upon n comma y for some n positive. So let us take this square and magnify it. So what we will get is something like this. So this is gamma of T naught. This is the open subset U, and gamma of delta, it lies outside. So this is Y. It lies outside Y, so it lies somewhere over here. Let's say it lies over here. So this point is gamma of delta, and this is gamma of T naught, right? But now, uh, notice that this line over here, it is in a different path. It is in a different connected component of U intersection Y than the component in which gamma T naught is contained. Right. So this means that gamma delta and gamma T naught are in different connected components of U intersected with C. But this is a contradiction, as uh, the interval T naught comma delta is connected, and so the images of all points, and so the image gamma of T naught comma delta is connected, and so has to be in the same, in one connected component. So this implies that gamma of 0, 1 is completely contained inside Y. So in particular, in particular, this means that the point 0, 1 can never be joined to a point, let's say 1 1, using a continuous path. So, uh, so in fact, it is easily checked. So it is clear, in fact, that y is path connected. So it is easily checked that c minus y is path connected, right? So this implies that c has exactly, and we just proved that a point in y cannot be connected to a point in c minus y using a path. So this implies c has exactly two path components. On the other hand, the closure of c minus y is equal to c. So this implies that, so c minus y is path connected, which means it is connected, and therefore its closure is also connected. This implies c is connected. So thus c is connected but not path connected. So we will end this lecture here.